about the different kinds of forces. And so you need to be aware of what those different kinds of forces are. We've already dealt with one, right? The normal force. The normal force is the force that is that you read when you step on a scale. Doesn't read your weight. It reads the normal force. I didn't break it. I'm like 5 pounds heavier than I was about 10 minutes ago. Explain that to me. Maybe I broke it. Anyway, the normal force, it means that it's perpendicular. Yeah.
I just want to explain again why the normal force is less whenever it's an incline.
Oh yeah, we're going to talk about that. Was that on your quiz?
No.
No.
I just was confused.
Okay. Yeah, so yeah, I'm going to get to that. Is that okay? I'm about to get that in just a second. That's a good question. Okay, so the normal force is perpendicular to the surface. That's what normal means. It's a mathematical term. It means perpendicular or an angle of 90 degrees. It doesn't mean usual or regular. It means normal, perpendicular at an angle of 90 degrees. And so the normal force is always perpendicular to the surface. Normally, we have a flat surface, a horizontal surface. Did y'all get that? Like that was a little. Yeah. Nobody got it, did you? Jillian is the only one, and maybe Caitlin. Normally, normally our surface is horizontal, and in a horizontal surface, that means that the normal force will be perpendicular. But not always. That sometimes we'll have an inclined surface, like right here. This is an inclined plane, and so there is a force. Hey, that's my wife. Did y'all know that? That's my wife in that picture. She what? Yeah, she's got the 40. She's strong. She's really strong. But that is an inclined plane. There is a normal force that's pushing on her back. Right? She's on the, what's this? What's this called? Leg press?
Standing leg press or like an incline squat.
Incline squat. Anyway, she's on this inclined plane. And there is a force that's pushing up on her back called the normal force. And so that normal force is right here, Fn. Okay, so there is also a weight. And this is getting to your question. Tell me your name again? Megan. There is a force due to weight. And the force due to weight is always towards the Earth. Always towards the Earth. So we have two forces. Normal force is always perpendicular to the surface, but not always vertical. The weight force is always vertical and towards the Earth. So the weight is always down in this direction. But you remember how we talked about that you can break vectors into their different components? I'll have a vector here that I can break it into two pieces here and here. Right? Remember we talked about here where if I step over there, then I can go to the same place by stepping here and here. And those are like the components of a vector. Well, I can do the same thing for that force weight. I can break it into its components. I can put one component right here, and then I can put another component right here. Those are those two vectors, the two yellow vectors, make up, they're the same as the weight vector. We talk about that in terms of displacement, like a little thing with the floor where I can get to the same spot by going one leg here and one leg there. But it's also true for any other type of vector. And remember, vectors are physical quantities that have two things. The first of those things is what? Distance, if we're talking about a different type of vector. Let's see, what did you say? Okay, direction is one of those things, and what's the second thing? Magnitude. Megan. Megan? Awesome. So, she said distance. And that is true if you're talking about a particular type of vector called the displacement vector. And the displacement vector has the magnitude, that's the distance, and then the direction. Okay? But like a force, it has a magnitude. It's just what is the force, the value of the force, and then also what is the direction. So vectors have two values attached to them, the magnitude and the direction. All right, so is this vector right here, is it bigger, smaller, or the same as the weight? Remember, it's a component of the weight. So, is it on there? It's smaller. That's right. So it's the components are always smaller than the vector. I'll write that down. So the components are always smaller than the vector. The components of the vector are always smaller. What is the third law? We have the law of inertia, that's number 1. Law of acceleration, that's number 2. What was number 3? Right, law of reaction. Sometimes we call that action-reaction. Where if I have one force, I have an equal and opposite force. So, I want you to notice here that I have one force that's in this direction. That's a component of the force weight. Is there a force that's in the opposite direction? And what is it? There is a force, but what is it? What is in this free body diagram, where I've drawn all the vectors, which force is opposite in direction to this force? The normal force, the normal force. So the normal force and FWY, that's what I'm going to call it, FN and FWY, that's this Y component of the force weight, are an action-reaction pair. Think third law, law of reaction. So, usually the normal force is equal to the weight. But here, the normal force is bigger, smaller, or the same as the weight. Now, I just told you that normal force and FWY are an action-reaction pair. That means they're equal and opposite, equal in magnitude, but opposite in direction. That's what the third law says, right? For every force, there is an equal but opposite force. So, is the normal force, we'll do it as a quicker question, is the normal force bigger than FW, less than FW, or equal to FW? A, B, C. Is the normal force bigger than the weight? That's A. Less than the weight? That's B. Or is it equal to the weight? That's C. For my wife, Kaisa, on the incline plane, the normal force that's pushing up on her, is that normal force bigger than her weight, less than her weight, or equal to her weight? All right, let's stop at 45. All right, so we have some that say it's bigger than the weight, some that say it's equal to the weight, and then the correct answer is B, that it is less than the weight. Well, that's okay. Remember, if you get it wrong, you still get credit. And honestly, if you get every question wrong in the quicker questions, if you just come to class, it's not a big deal. All right? So, a couple things we put together. One, that this is a component of the weight. Components are always smaller than their vector that they make up. So FWY is smaller than the weight. And then 2, FWY and FN are an action-reaction pair. I can tell that because this one's in this direction, and this one is in the exact opposite direction. So they are an action-reaction pair. And because they're an action-reaction pair, they have to be equal in magnitude. Opposite in direction, but equal in magnitude. So that means Fn is equal to the negative of FWY. And since FWY is smaller than FW because it's a component, the normal force in this case is less than the weight. Megan? You follow me? Okay. That's an important idea, that our normal force will decrease if your weight, it will decrease if you're inclined plane, if you're on an inclined plane. So, for example, let's say that I weigh 700 newtons. So what if Fw is 700 newtons? If I stand on a scale like this, it'll read 700 newtons. But if I stand on a scale like this, so I put my scale on an inclined plane, then it'll read something less than 700 newtons. Normal force is less on those. Let's look at different types of friction. Right, your book had a section on different types of friction. There are two types of friction that we'll worry about, and that is static and kinetic. You can probably tell from the words that one is related to two objects that are not moving, and one is related to two objects that are moving. Which one's not moving? Right, so static is not moving. Kinetic is moving, or I like to think of it not as moving, but as sliding. So if I have two surfaces that are sliding with respect to one another, then that is kinetic friction. So the kinetic, I'm going to call sliding friction. Now, I can calculate both of these in a particular way. First of all, I'm going to let friction be stripped F like that. So it's a force, so I use the letter F, but it's a special type of force that we see a lot, and so I'm going to use a special letter F, just a script F, lowercase script F. It is equal to mu times the normal force. This is the Greek letter mu. Mu. Sorry. It's transliterated mu. Mu. Like phi mu. Need phi mu's? Phi mu. Right? Although this is the lowercase phi mu, whereas phi mu uses the uppercase. So it looks like a U, or maybe it looks like an M, but it's really a U with a little tail on the side. Those Greek letter mu. So a couple of things I want you to notice that is dependent upon two things. One of them is the normal force. Bailey? How many Baileys I have in here? There's another Bailey, right? Are you already raise your hand? Maybe you're a little one. Alright, so this is a sheet of paper. Can you put your hand on it like that? If she puts her hand on it, she's pushing down on the sheet of paper. What is she creating between the paper and the desk when she pushes down on it? Not directly. She's creating another type of force. When she just pushes down directly vertically on the desk, what is she creating between the desk and the paper? What type of force? No. Normal, yes. So she's pushing down and creates a normal force that pushes back up. All right, let's push down. Now, if I pull, I can move the paper so that goes. But if she's not holding on, there's very little friction. There's a little bit of friction. Now push back down. Would you try to keep me from pulling? One of us is going to win. Please, all right. Okay, so if I increase the normal force, that increases my friction. So if Fn goes up, that means that the frictional force goes up. And a good example of this, if I have an object, like my sheet of paper, for example, there are some forces at work here. There is the weight. Remember, Fw is equal to m times g, right? You all recall that? So if I have a 2 kilogram mass, what is its weight? 20, yes, because g is equal to 10 meters per second squared. I just multiply that. So when we talk about mass and weight, those are two different things, but they're related. They're different by a factor of 10. Mass is the amount of matter in an object, or even better, mass is a measure of what? Inertia, right. The tendency of an object to stay in its current state of motion. That's really what mass is a measure of. It's not really a measure of how much matter is in the material, though it is related to that, of course. It's really a measure of what is the tendency of it to stay in its state of motion. So that's the weight. And then if I have the weight, then I'll also have a normal force, Fn. But notice what happens if I apply an additional force here. Then what will happen to the normal force? Will it decrease, increase, or stay the same? Push down just a little bit. All right, now push down really hard. It's going to do what? I'm just hearing this. What do you think? It's going to increase. Now the normal force, if I push down just like she was doing, she's pushing down, it increases the normal force between the object and the surface. So now my normal force is not going to be like this. It's going to be much bigger than it was before. Okay? In fact, if I were to calculate Fn, I would say that Fn is equal to Fw plus F. Because I've added in this extra little force here. Before, Fn was just equal to Fw. But when I add in this force, I have to add in that amount for the normal force. I've increased it by that amount. Okay, so the friction is dependent upon the normal force. The friction is also dependent upon this Greek letter mu. Mu is the coefficient of friction. Your book talks about this value. It's pretty important. It changes between surfaces. So if I have two surfaces, metal and ice, that come together, those have a relatively high or low coefficient of friction. Metal and ice. High or low coefficient of friction? Low, right. Because metal and ice, they slide really easily with respect to one another. Been ice skating before? Metal and ice? That's why they use metal on ice, because you can slide across it very easily. But if I have, for example, rubber on wood, a relatively high or low coefficient? High, right. So some surfaces have more friction, just because the way the surfaces interact with one another. It's not necessarily the smoothness of the surfaces, because rubber is pretty smooth, right? Rubber, if you have like a rubber tire or like just a piece of rubber, that's a fairly smooth thing. But if I rub it up against a piece of wood, then that's going to be a lot of friction, just because of the types of material that they are. Not because they're smooth. It doesn't really matter that much. It matters some, but not that much. But the types of material. Now, there are two types of friction, static and kinetic. And so there are also static coefficient of friction and kinetic coefficient of friction. There's a difference between the forces of friction if the object is moving or not moving. And you've experienced this before. Have you ever moved furniture across your floor? Like a big piece of furniture, like a couch or a dresser, and you push and it doesn't move, but then after you get it moving, is it easier or harder to keep it moving? It's easier, right. So whenever you're moving something big, it's always harder to get it going. And that's because which of those, static or kinetic, is bigger? Which friction has a larger value? The static frictional force or the kinetic frictional force? Static, right. So when I'm pushing a piece of furniture, I'm trying, and I can't push it, right? But then, after I get it going, it's much easier to push. Have you experienced this before? Let me show you another way that you can experience it. You can do this today if you like. It's probably going to blow your mind, because I know that you've never done this before. When you leave today, you go up Maywood, is that right, most of you? To get up onto Highway 1? When you leave, I want you to do something that you've never done before. Are you ready to hear it? Huh? What? I want you to do something. It's gonna, wow, I didn't know you could do that. I want you to stop at the stop sign up at Maywood and Highway 1, okay? If I come to a complete stop, you understand what I'm saying? Huh?
Not a rolling stop?
Not a rolling stop. Come to a complete stop. You know how your brakes work, right? You have a rotor that spins, and then you have two brake pads that clamp down onto the rotor, right? And so when the wheels are moving, what type of friction is at work between the brake pad and the rotor? Kinetic. When the wheels are rolling, you have kinetic friction between the rotor and the disc in the wheel. What type of friction do you have when it stops? Static. Remember, there's a difference between kinetic, an actual difference in the value of the kinetic and the static friction. So if you come to a complete stop today at Highway 1, which is a good idea, what's going to happen to your car? No, you keep your foot on the brake. Don't let it roll back. Okay. Come to a slow stop when you're leaving out on Highway 1, a slow stop, and you'll feel the car will just sort of jerk a little bit. It'll sort of lurch forward, and that's that transition going from static to kinetic friction. Or excuse me, sorry, going from kinetic to static friction. Because there's a difference. There's a discontinuity between those two values, and that's why your car just sort of lurches forward a little bit. You try it. And then to your neighbor in the car, you say to them, hey, static and kinetic friction, they're different. And that's why there's a discontinuity between the coefficient change of kinetic and static friction. Y'all got it? Okay. Okay. By the way, you don't need to write this down, but it's kind of interesting. Do you know what type of friction acts between a rolling tire and the road? You're right. Why did you say static? Oh, was that in the book? Okay. All right. Did they talk about anti-lock braking systems? No. Okay. Well, this is interesting. My dad worked at a tire shop all my life, and so as a kid, my brothers and I, we all had to go work at the tire shop too. We would mainly sweep the floors, but we'd change tires, and like my brothers got older, they did like front end alignments and brake jobs and stuff. My dad didn't let me do that because he said that my brothers both dropped out of high school. He said they didn't want me to drop out of high school, and he thought, well, you just sweep the floors, and you don't need to learn how to do brakes and alignments. And it was a wonderful gift that my dad gave to me. Isn't that awesome? That he would have that foresight. He's an awesome, awesome guy. But anyway, anti-lock braking systems. What they do is that they keep your tires rolling. They keep your tires from locking up. Because if your tires lock up, that means that you go from static friction with a rolling tire to if the tire stops rolling, then it's a sliding friction or kinetic friction. But what kind of friction is bigger, static or kinetic? Static. And so you want static friction to always be at work in your car. So used to, if you have an old car, if I have an old car, like sort of pre-80s maybe? No. Used to, they didn't have anti-lock braking systems. And so if you wanted to stop in wet or icy conditions, what do you have to do? You had to pump your brakes, yeah. So you had to pump your brakes really fast so that the wheels didn't lock up, but you would still slow down. Yeah. I know, it seems archaic, doesn't it? But now we have these systems in our cars where it does the pumping for you. So when you slam on the brake, your brakes say, no, 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 no. I don't need to do that. Instead, it goes, and it pulses your brake pads so that your wheels don't lock up. They keep spinning, they just slow down. Did you know that? Did y'all know that? You three ladies? Okay. Did you know that? Okay, let's pay attention or read. Okay? All right. So that's friction. Tension is used, we talk about in this chapter only really to redirect forces. So tension Oops. You can use ropes and cables to redirect forces. All right, and we talk about this because you have lots of ropes and cables in your body in the form of muscles and ligaments that redirect forces. That they'll take a force that's maybe applied up here and make it go applied down in this direction. Or take a force that's applied here and redirect it so that you get motion in a different direction. And so we'll just think of tension in a way of redirecting forces. All right? Tension is a little more complicated than that, but we'll just stick with that. That we use it to redirect forces. And so, for example, if I have a force that's applied over here, then I can attach a rope or cable or whatever. This is my rope or cable. And then I can apply that same force over here. So if I have a force here, I can redirect it to have the same force over here. Likewise, if I put it over a pulley or over some surface like this, if I apply some force over here, say F is equal to 5 newtons, then I'm going to experience that same force over there. I think you had a question on your quiz about that, didn't you? Yeah, so the one with the foot and the mass attached to it, that if I have a 2 kilogram mass attached on that traction system, the one on your quiz, then that means I'm going to have a 20 newton force applied to the guy's leg, which they use to sort of set it into place. Ever seen a traction system? I think some of you have, right? What I'm talking about. There's a picture of it on the quiz. All right, so the thing about tension is just used to redirect forces. All right, let's do a couple of clicker questions. We'll do the one on the left first, and then we'll do the one on the right. Everybody's gotten the workbook from the bookstore, is that right? Okay. All right, let's do about 10 more seconds. Before this is the one on the left. Force in your bicep. What is that called, that force? I'm going to stop at 45. Oh, look at that. C is right. That's our tension force. Hey, why do cows make great scientists? This is where you say, I don't know. Because they're always outstanding in their fields. All right, so tension is right. And then Newton's third law, which one is that? We'll be able to identify the laws. All right, let's stop at 23. 23. Only that A is right. The third law, for a force, there's an equal and opposite force. That's our action, the action force. And by the way, this is our second law, right? The acceleration. And this right here is our first law. So on the upcoming tests, we might see those sort of restated in slightly different ways, but they'll still carry the same idea. That the first law has to do with this inertia and staying in the current state of motion. The second law has to do with the law of acceleration. That's the whole F equals ma bit. And then the third law is all about action-reaction. Remember, too, that if I apply a force to an object, no matter the relative size of the object, like if this thing was 1,000,000 pounds and I pushed on it, it would push back on me with a bigger or smaller force? The same. Oh, yes. That was tricky, wasn't it? Like I didn't give you the right answer. It would push back on me with the same force. Just like the Earth and the moon is a lot smaller than the Earth, but they tug on one another with the same force. I'm a lot smaller than the Earth too, but you know what? I pull on the Earth with 700 newtons of force. just like the Earth pulls on me with 700 newtons of force. All right, good job. Let's look at torques. Torques are pretty important to the body because there's a lot of different torques that apply in the body with muscles. And then also we see torques in a lot of human performance type things, like lifting weights and, physical things. Forces cause acceleration in a line. Remember that's F equals ma. Torques cause it in a circle. And when I say it, I mean acceleration. If I apply a force, it causes something to move in a straight line. If I apply a force, it moves in a straight line. If I apply a torque to something, it will cause it to move in a circle. So for example, I can apply a force, a torque like this, and cause this thing to move in a circular path. I'll define what that torque is. Torque is equal to, torque, we'll use the Greek letter tau. It just has a squiggly line on the top. And torque is equal to F times R times sine of theta. You've probably seen sine, various trig functions in high school, but I know it's probably been a long time. And in fact, you're not really going to have any trig functions. If you look on your equation sheet, the way that I give this equation, and the way that you should really be familiar with it, is that torque is equal to F perpendicular times R. If I think about, I have an object that's allowed to rotate about a certain point. So this is the fulcrum, the triangle. If I apply a force to this, I apply it perpendicular to the surface, and then are perpendicular to what we call the moment arm, and then this distance is R. This is called the moment arm. Or sometimes people just call it the moment, but R is the length of the moment arm. The moment arm is always the distance from where the force is applied to where the axis of rotation, or the fulcrum, is. You have the force and R. So in this case, for example, my axis of rotation is like right here, right, where the chair rotates around the seat post. So if I apply a force right here, my force is whatever force I'm applying here, and R is the distance between the axis of rotation and where I'm applying the force. Okay? Now the whole sine theta comes in. Theta, we won't spend long on this, but I just want you to understand, because it does come up a little bit later when we talk about the deltoid. Theta is this angle. Theta is the angle between the force and the moment arm. Theta is the angle between the force and the moment arm. Angle, that's the symbol for angle, between F and the moment arm R. You get maximum torque if that's equal to 90 degrees. And in fact, the sine of 90 degrees, $30 to somebody who can tell me. No, I'm joking. I'm not going to give you $30. What is it? No, what's the sine of pi over 2 is the same as 90. That's good. It's not 5 or 6. Yeah. What's the sine of 90? You can probably think about it looking at these two equations and tell me what the sine of 90 degrees is. Not 0? No.
Wait, hold on.
It is 1. Yeah. All right, so the sine of 90 is equal to 1. And so if this is 90 degrees, a sine is always 1 or less. Any trigonometric function is always 1 or less. So the sine of 90, if that's equal to 1, that's the most it can be. So you get maximum force when your angle is equal to 90 degrees. If your angle is small, I mean, if your angle is less than 90 degrees, then you're going to get less and less force. I'm sorry. If your angle is less than 90 degrees, then you'll get less and less torque. Illustrate for you. But what's another way to get smaller torque? I can change the angle. What are some other ways to make my torque less?
Push on like the door closer to the hinge.
You're right. I can make R smaller. Or what else? I can change theta. I can change R, or I can change F. Right. So if I have a smaller force, I get a smaller torque. So as Caitlin said, that if I apply a force right here, which is really far from the axis of rotation, then I get a big torque. That's why most people, when they open the door, they use this part of the door. Now they don't push on this part of the door because it's really hard to open the door down here. I can do it, but it's a lot harder. Listen, today, as you go around the building, whenever you come to a pushing door, I want you to try that. Instead of pushing here like normal people do, I want you to push here. And just try to get the door. You'll get it open. Don't worry, you'll get where you're going. But it's going to be a lot harder. And that'll remind you that the torque is dependent not only on the force, but also on the length of the moment arm. Now, the other thing is the angle. Now, I can apply a force here, right? And I get a pretty good torque out of a big force, big R, theta is equal to 90 degrees. But what if I tried to apply a force at an angle like this? Is it easier or harder? It's quite a bit harder because my torque is smaller. I have an angle that's less than 90 degrees, a shallow angle, and so it makes it harder to open this door. So you can either do one of those as you go about. That's your homework for today, is that as you go through doors, you can push at the hinge or really close to the hinge, or try to push like this. And then when people laugh at you, just don't mind them. Just say, go on by. I'm doing what I'm doing here. It's for a class. That's what your deltoid does, right? Your deltoid is attached to your upper arm, correct? You'll have anatomy. You know better than I do, right? Most of you have. Is that right? How many of you have anatomy? Who has anatomy? Brian, you have anatomy? Anybody else? Grace, you have? Yeah. Okay. Don't worry, I'm going to give you what you need. I don't really know that much about anatomy either, Brian, so don't feel bad. But everything's in the book that you need, and I'll give it to you. Anyway, your deltoid is attached to your upper arm at a really shallow angle. And so that's what it's got going against it. That it's trying to lift this big old arm, you know, like trying to open the door, pushing at a very shallow angle. That's why your deltoids are so big, right? Right? They have to be strong in order to do this type of motion. All right. So torque is equal to F perpendicular times R. The units of torque are Newton meters. You'll see other units of torque. Foot pounds. You know, here's a torque wrench. You know what a torque wrench? Excuse me. You know what a torque wrench is? Yeah, a torque wrench just. It's a wrench. Sometimes you have bolts or nuts that you want to apply a certain amount of torque to, and if you apply more than that, they can shear off, or maybe they're not tightened properly. And so it tells you how much you're tightening a bolt or screw or whatever. And so a torque wrench will actually tell you how much torque you're applying. And that's usually in the United States in foot pounds, right? Foot is a measure of what value? The force or the moment arm? Moment arm, and pound is a measure of what? Force, right. Okay, so, but we'll use Newton meters. When not rotating, an object is said to be in equilibrium, and the net torque is 0. When not rotating, the net torque, we've used that word before regarding the forces, the net torque is the sum of all the torques. And not just adding them up, but we have to add them up like vectors. We'll add them up so that some torques are in one direction, other torques are in another direction, and we'll have to add those up properly, just like we did for forces. Remember when we did net force? If we had one force in one direction, another force in another direction, we had to take the difference. The vector sum was actually the difference. All right. let's just do a quick calculation. I'm just going to sort of do a quick little thing just to illustrate to you how we calculate torque. Let's say that I have an object. Say it's rotating about this point. Let's say that that object is, I don't know, 1 meter long. And let's say that I apply a force equal to 3 newtons. If I want to figure out the torque, I would say that the torque is equal to F perpendicular times R. Notice that my force actually is perpendicular. And so it's going to be 3 newtons times 1 meter, or 3 newton meters. All right? Now we can apply that in a more complicated system, like a seesaw, for example. And this is similar to a seesaw. Well, it's a pretty big seesaw. It's like 12 feet long. So I have a seesaw, or a lever. I have a mass on one end, and I want to know what force I need to apply on the other end in order to set this thing into equilibrium. All right, so if I were to apply a force down here, what would that force need to be in order to hold this object in place? So if this is my, oh no, I lost it. This is my lever. I have a mass that's on this end, right, pulling down. I want to know what force must I apply on this end. And my own strength. Where did they go? You see that coming later makes you wonder. I think that you saw that coming. All right. All right. So if I'm applying a if I have a mass on this end, some sort of weight, I want to know what force must I apply on this end in order to make it balance, to make it be in equilibrium. Pretty easy, right? Do y'all know what that force would be? A kilogram isn't a force, that's a mass. 20 newtons, right. So the way I would do this is I would say, well, I have my guy here. I have a 20 newton force. F is equal to 20 newtons. This is equal to 2 meters. And I want to know what force must be applied over here. I'm going to call this side torque L. So like the torques on the left-hand side, that they have to equal to the torques on the right-hand side. All right? Because then that would be that the sum of the torques will be equal to 0. Because I would say torque left minus torque right is equal to 0. Torque left is causing rotation in one direction. Torque right is causing rotation in the other direction. And so that's why I think the difference. Torque left, what direction is it causing motion in? Is it clockwise or counterclockwise? You're right. So if I just have this force, it's going to cause this thing to rotate in the counterclockwise direction. Typically, we let counterclockwise be positive. This force over here is going to make it rotate clockwise. And typically, clockwise is negative. I don't know why, but clockwise is, I do know why actually, but clockwise is negative in our system. It's because we live in a right-handed coordinate system. And it's just how we define clockwise rotation. No, really, it's because the world hates left-handed people. Did y'all know this? I'm left-handed, so I can say that. Who else? Okay. Somebody back there, right? You're, what's your name? They hate us. Bad. They make right-handed notebooks, right-handed scissors, or left-handed scissors. Huh? There's no left-handed desk in this room. We got those desks. And, you know, that's not really meant for left. That's for handicapped people. That's how they view us. That's handicapped. We have a handicap. Crazy, right? Can I take a little aside? Since all the left-handers here are women, is that right? Do you know that one in 10 guys are left-handed? It's not a big deal to be a guy and be left-handed. But 1 in 100 women are left-handed. So it's remarkable that we have 3 or 4 left-handed women in this room. That's kind of a big deal. That's like not normal. All right. So if I wanted to figure this out, I would say F times R on the left is equal to F times R on the right. And this is 20 newtons. This is 2 meters. FR, 2 meters. So FR has to equal to 20 newtons. All right? Listen, you'll do some math in this class. You won't do a whole lot, but you'll sort of do about this level of algebra, being able to solve that equation for FR. By the way, how would I go about solving it for FR? What now? That's right. I divide both sides by 2. That cancels out. That cancels out, and I'm left with FR equals to 20 newtons. All right? Let's say, for example, instead of my force being there, I wanted my force to be here. First of all, I'll call this F1, and I'll call this F2. The reason I'm calling it F1 because it's going to be at a distance of 1 meter. First of all, is F1 bigger than F2, smaller than F2, or equal to F2? A, B, C. In order to have equilibrium, I can put a force of 20 newtons down here. What if I put my force here instead? Is that force going to be bigger, smaller, or equal to 20 newtons for this F2? Yeah, ABC. Feel free to ask your neighbors, okay? Y'all are about half and half right now, so ask your neighbors. It's not equal, I'll tell you that. Feel free to ask your neighbors. Right foot. All right, let's stop at 53 or 54. Hey, have y'all ever gone to the seesaw with a little kid? And you put a little kid on the end of the seesaw, and where do you sit? Do you sit out at the end of the seesaw, or do you have to scoot in up towards the middle? Right. Do you have a bigger or smaller force than the kid? You have a bigger force, right? So if you're with a kid, a 2-kilogram kid, like a 5-pound kid, you put like strap a little infant. But if you had a kid here, you would have to sit in the middle of the seesaw because your force is bigger. So F1 has to be bigger than F2. So A is the right answer there. I'll show you all the answers. Is that right? Yeah, F1 is bigger than F2. Y'all follow me on that? Let me show you how to work out the math. You get the seesaw, right? Y'all have had that experience with a kid on a seesaw? Listen, if you haven't, just go over to Pelcher Park, grab some kid, and say, hey, this is for my class. We need to go get on the seesaw. And make sure that's a kid smaller than you, okay? Because otherwise it won't work, like if the kid's bigger than you. All right, so what we're going to do here, here's my seesaw. I have 20 newtons here. It's applied at 2 meters. And now I have another force applied at 1 meter. And I want to know what this force is. So I would say torque on the left is equal to torque on the right. That is 20 newtons times 2 meters. Because you know, torque is F perpendicular times R. And in this case, the forces are perpendicular. Is equal to FL, that's the force I'm looking for, times 1 meter. So that means FL has to be 40 40 newtons. All right. It was simple here because I divide through both sides by 1, but any number divided by 1, of course, is itself. So it's just equal to 40 meters. And also notice that when I divide it through by 1 meter here, the meters cancel, because I'm just left with newtons. So I know then that my dimensions are correct in this. I would expect a question like that, where I ask you, I give you a system with a force, and I ask you what force has to be applied to set this thing in equilibrium. Okay? I can do that for me? Of course you can. Let's do a couple of quick tests. Do the one on the left first. Feel free to ask your neighbor. I've lost like 3 pounds since I left. See, you can't measure your body weight every 10 minutes because it changes in the scale. How is a torque similar to a force? All right, let's stop at, I don't know, 55. Go ahead and do the next one. But we're doing the one on the left right now. 55, we'll stop. Hey, yeah, all right. B is right. What was D? The torque and force both have units of newtons. This is almost right, because force has units of newtons, but remember, torque doesn't have units of newtons. It has units of Newton meters, right? It's a force times the distance, times the length of that moment arm. So B is right. The torque changes the rotational motion. The force changes the translational motion. Let's do the one on the right. Torques are relevant in which of these types of motion? All right, let's stop at 32. You are awesome. D is right. What do you do if you're attacked by a gang of clowns? This is good practical advice. Go for the juggler. Have a great day. And look, I think we're out early. Woo! Don't say I never did anything for you. Thank you. I don't know when the next one is going to be, but I'm pretty sure. All right. We might just move on ahead to chapter 2, but you should be reading in the book regardless. All right.